Hi everyone. So in the last lecture we were studying about basic gates, right? We studied AND gate, we studied OR gate, and we studied about NOT gate, and we studied about buffer. Now we are going towards the universal gates. So this is the first universal gate, which is NAND gate. So how NAND gate is made of? AND plus NOT. So there will be an AND gate and then there will be a NOT gate. So that is our universal gate. AND gate plus NOT gate. So AND plus NOT, that is known as universal gate. So what will be your Y? Y will be A into B bar, right? First AND operation, A into B, AND operation, and then bar. Okay. So Y will be AB bar. Y will be AB bar. And what did I tell you? De Morgan's theorem. Do you remember? So AB bar can be written as A bar plus B bar, because there is dot in between. So if you want to replace dot with plus, then you can take individual bar. So A bar plus B bar. Now A bar plus B bar, how it can be made? Look, this is A. Then I make this bar, because I told you our inverter can be simply replaced with a simple bubble, right? So it's a simple bubble. So here A bar is going and here B bar is going. And what is this? This is OR gate. So what OR gate does? It will simply add. So A bar plus B bar. So both are equivalent only. Instead of OR, I should make this arrow. This is the arrow of equivalence. So both gates are equivalent only. So and NAND gate can also be called as bubbled OR gate. Bubbled OR gate. Bubbled OR gate. Because these are the bubbles there, which is A bar plus B bar. So AB bar can be written as A bar plus B bar as well. What will be the truth table? 0 into 0 is 0, and then you take the bar. First you do the multiplication and then you take the bar. 0 into 0 is 0, 0 bar will be 1. 0 into 1 is 0, 0 bar will be 1. 1 into 0 is 0, 0 bar will be 1. 1 into 1 is 1, 1 bar will be 0. So this is the truth table. Okay. Now in the examination, if someone asks you, or in the interview if someone asks you what is a NAND gate, what you will say? So NAND gate is the gate where output will be logic low if all the logics are high. If all the input logic are high, output will be logic low if all the input logic are high. If any of them is 0, if any of the input logic is 0, then output will be logic 0 only, right? Because let's just say this is my input A, B, C, and my output is going from a NAND gate. So what will be my output? A, B, C bar. If any of them is 0, let's just say this is 0, then A into B into C will be 0 only. 0 bar will be 1. Okay. So my output will be logic low if all the logics are, or if all the input logic are high. Okay. So this is the definition of NAND gate. What will be the switching circuit? Here you can see this is the switching circuit. Y is equals to AB bar. This is the switching circuit. This is the 3 input NAND gate. 3 input NAND gate. You can write down the truth table on your own. Here I am not making the truth table. You can certainly write down the truth table on your own as well. So how it can be implemented? This bubble comes here and this AND gate will be replaced by OR gate. This is how we will remember. Bubble will come here. So 2 bubbles are there and this AND gate will be replaced with OR gate. That's it. Bubble comes here and AND gate is replaced with OR gate. So here what you will get? A, B, C whole bar. So certainly here it is A bar plus B bar plus C bar. So this A into B into C bar can be replaced with A bar plus B bar plus C bar. So same thing you are getting here as well. Okay, so this is another way of representing it. Let's see NOR gate. So OR plus NOT. First there is OR gate, A plus B, and then there is a bar. So how you can replace this? If you take individual bar, then plus will be replaced with dot. So A bar dot B bar. Then what will happen? This bubble comes here, this bubble comes here, and your gate, OR gate is replaced with AND gate. So NOR gate is called as bubbled AND gate. Okay, NOR gate is called as bubbled AND gate. So it can be replaced at A bar dot B bar. Okay. Now let's do the let's write down the truth table, that is A plus B whole bar. So 0 plus 0 is 0. 0 bar is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 bar is 0. 1 plus 0 is 1. 1 bar is 0. 1 plus 1 is 1. 1 bar is 0. So in NOR gate, output will be logic high if all the inputs are logic low. Okay. In NOR gate, output will be logic high if all the inputs are logic low. So in the examination, if they are asking you the definition, then quickly you will write down the truth table, and based on that you will tell the definition. Okay. And this will be the switching circuit. How it will be the switching circuit? Because both are in parallel, so it would be A plus B. And since it is connected parallel to the output, so there will be bar. So this will be your switching circuit, right? For 3 input, certainly this bubble will come here, and this OR gate will be replaced with AND gate. So this will be your output. So here, how can I write the output? A plus B plus C whole bar, or it can be replaced with A bar dot B bar dot C bar. What about this one? A bar, this is A bar, and since this is AND gate, so A bar dot B bar dot C bar. Okay. Now this is the most important question, and listen it very carefully. Why NAND and NOR gates are called universal gate? So let's read down the first point. With the help of AND gate, OR gate and NOR gates combined, you can design any Boolean function. Let's just say I give you AND gate, OR gate and NOT gate, and then I ask you design a random Boolean function. Let's just say this is the random Boolean function I am giving you. This random Boolean function I am giving you, and I will ask you, can you design this Boolean function using these 3 gates? You will say yes, I can design any Boolean function using these 3 gates. So that's why they are called basic gates. Now if I say I am giving you only AND gate, and I ask you to design this thing. So are you able to design this particular expression using only AND gate? So your answer will be no. I need 3 gates there, AND, or NOT. Actually, you need only 2. You need AND gate and NOT gate, or you need OR gate or NOT gate. So if you have these and these with you, basically these 2 you need. With AND and OR, with these 2 gates you will not be able to design this, because from where will you get this bar? So for bar you need NOT gate. Okay. In the further part of this chapter only, I will tell you that using only 2 gates only, AND and NOT, or OR and NOT, you can design any Boolean function with the help of only 2 gates. But you certainly need NOT gate. So what did you understand here? Alone basic gate is not enough to design any Boolean function. If I only give you NOT gate, so NOT gate can only do bar, nothing else. It cannot do addition, it cannot do multiplication. So only one gate is not enough to make any Boolean function. You need these 3 combined, or at least these 2 or these 2, right? So at least 2 you need. So alone they are not enough to make any Boolean function. But if I give you only NAND gate, and then I ask you, can you design this function? Then your answer will be yes, I can design this function. So only NAND gate is enough to design any Boolean function that is present in this whole universe. Or here I will type, I should not write OR because OR is also a gate. So what should I write? In smaller letter I am writing OR. Or if I give you only NOR gate and I ask you, can you design this function? Then your answer will be yes. So alone NAND gate is enough to make any Boolean function. Alone NOR gate is enough to make any Boolean function. So that's why they are called universal gate. They are not called universal gate because they are alone not enough. AND, OR and NOT are not alone enough to make any Boolean function. But NAND gate alone is enough to make any Boolean function. From NAND gate you can make NOR gate as well. From NAND gate you can make AND gate as well. From NAND gate you can make OR gate as well. From NAND gate you can make NOT gate as well. Basically from NAND gate, if you can make these gates, then certainly using only NAND gate you can implement any Boolean function. So are you getting the point? What is the condition? That if you are using basic gates, then you need at least 2. And in those 2, one has to be NOT gate as well. That means you need NOT and OR, NOT and OR, NOT OR. NOT and this is one of the possible combination. NOT OR, this is another combination. So you need at least 2. They alone are not enough. But if you are given only NAND gate, then it is alone enough to implement any Boolean function. That's why they are known as universal gates. Okay. So here I will write alone enough to implement any Boolean function. That's why they are called as universal gate. Okay, let's see this. Now from NAND gate we will design AND gate, OR gate and NOT gate. We will design other gates as well, but later on this chapter. Okay, now using NAND gate we will design AND, or NOT, and then using NOR gate we will design AND, or and NOT. Okay, so let's see this. NAND gate as universal gate. So first we will design NOT gate using AND gate. So what do you need? A bar you need. Okay, so what I do, I simply take this one NAND gate only, and both of the input I connect with single A only. So here A will go, here also A will go. What will be your output? A into A and then bar. What is A into A? A into A is A only. We studied it in Boolean algebra. We studied A into A into A into A will always be A only. So A into A is A only, and then there is a bar. So NAND gate, from NAND gate you got OR gate. By only using one NAND gate you have designed NOT gate. Understood? Now what you need to design? You need to design AND gate. So what AND gate does? A into B. This is our target. Our target is to design this thing. Our target is to design this thing. So if I put A here and B here, what will be my output? AB bar, right? This is my output, AB bar. My output is AB bar. Now what I need to do? I am having AB bar. Now if I take another bar, then what will be my answer? AB. And this is what is required. So for another bar, what I need to do? I need to use an inverter. But I directly cannot use an inverter. I cannot use this. I need to make it using NAND gate only. So I will use this structure. Are you getting this point? I will simply take this structure. This AB bar goes here. This also AB bar goes here. So what will be your output? AB bar dot AB bar, multiplication of both, and then whole bar. So AB bar dot AB bar will be AB bar only, and then there is whole bar. So AB bar and bar will be AB only. Are you getting this point? First A into B, AB bar, and then whole bar will be AB only. So first there is an AND gate, and then there is an inverter. Now you need to make OR gate. What do you need to make? OR gate. We will see this topic again. Here my target is only to show you that they are working as universal gate. I will give you an intuition how you can make any kind of gate using NAND gate. This topic will come, okay, and it will be very interesting. In the next lecture only you will see how to design any Boolean function with using two input NAND gate and NOR gate, and with minimum number of gates. Using minimum number of gates, that also you will see. Now what is our target? Our target is to design y is equals to a plus b. This is what we need to design, right? Y is equal to y is equals to a plus b. So a plus b, but using what we need to use? We need to use NAND gate, right? So what I can do? Look, now you will have the question, sir, how did you think of it? So I know it. That's why I thought of it. But I will give you the intuition. But in the next lecture. Okay. So first what I am doing, I am getting a bar here. What I am doing, I am getting a bar here. Second, what I will do, I will get b bar. This will give you A bar and this will give you B bar. Now what do I know? That this AND gate can be replaced with a bubbled OR gate, right? Bubbled OR gate. Here I am having A bar and here I am having B bar. So if A bar goes here, so A bar and then another bar, it will become A only, and B bar then another bar, it will become B only, and then there is OR gate, so plus will come. That will be our output. Did you understand this point? Here what I am going to make is that this is NAND gate only. Say yes or no. This structure is of NAND gate only, right? This is NAND gate only. This is A bar and this is B bar. So Y is equals to A bar bar plus B bar bar. It would be AB. Sorry, A plus B. A plus B. And this is what you wanted. So this is a NAND gate only. Understanding this point? I hope you must have understood. So better we should replace this with this. We should replace this with this structure only. With this structure, okay. So the same structure I will be replacing it, not with this one. So I will remove it. Look, what will be your Y if I only replace this with this structure. So A bar dot B bar and then whole bar, right? And then whole bar. Now there is dot in between. If you want to replace this dot with plus, what you will do? You can take individual bar. A bar, then individual bar, plus B bar and then individual bar. So A plus B. That's your answer. So your answer is A plus B. Okay. Now let's see NOR gate as an universal gate. So what you need to do? You need to make an inverter. So same thing I will do. Inverter means NOT gate. So same thing I will do. Y is equals to A plus A bar. So you will get A bar. Now you need to make OR gate. So how will you make OR gate? What is our output? Our target is to get A plus B. This is our target. So from here what I will get? So let's make it. So first I am having A and B with me. So first what I will get? A plus B bar. First I will get A plus B bar. And then I will simply make an inverter. So how will I make an inverter? By using this structure. So A plus B bar goes here, A plus B bar goes here. Both are added and then there is one more bar. So it would be Y is equals to A plus B. Now I need to make AND gate. So what is my target? My target is to make A into B, right? So let's just say how I will design it. Let's see. So first this is my A. If A goes here, what will be my output? A bar. And then B goes here, what will be my output? B bar. A bar, B bar, right? Now I know one thing, that this gate can be replaced with this gate as well, right? This is how also it can be replaced. So here I am having A bar and here I am having B bar. So A bar and then bar, it would be A. B bar and then bar, it would be B. And since this is AND gate, there will be multiplication. So AB, this is what I am getting. So here I am just replacing this structure. A bar, this is your A bar and this is your B bar. Bar of A bar, A. Bar of B bar will be B. A into B will be AB. So better I need to show with the same structure only. So that's how I will show it. So y is equals to A bar plus B bar. Here first we will do the addition and then take whole bar. So let's assume A bar as x plus y bar. B bar I am assuming as y. X plus y bar, what it will be? X bar dot y bar, right? X bar dot y bar. So A bar and then bar dot B bar and then bar. So A bar and bar will be A into B. So y is equals to AB you are getting. Okay. So y is equals to AB. This is the AND gate I am getting. So this is how I am using AND gate as an universal gate. Now we will study about arithmetic gate. Okay. There are a lot of things in those universal gate, but once we study arithmetic gate, after that we will move towards those points. So I am not going to skip anything. Everything that is there, that is necessary for your examination, that will be there. Okay. So first let's study about arithmetic gate, then we will come back to universal gates. So I have to pause the video because I have to change the slides. So I will continue now. So let's see our first arithmetic gate, that is EXOR gate. So there are two arithmetic gates, EXOR gate and EXNOR gate. Okay. So we will see it one by one. We will see all the properties and everything. So EXOR gate. So output will be logic high when both inputs are different and output will be logic low when both inputs are same. So this thing is written for only two inputs. It is written only for two inputs. So generally in the interview you will not say this thing. In the interview you will say this thing. What you will say in the interview, that I will tell you. So in the interview you will not say that output will be logic high when both inputs are different. What you will say in the interview, that I will tell you. But let's just write down the output expression for two input. So that would be A bar B plus A B bar. Bar of one and then another one on its own plus A and then the bar of another. It can be replaced with the A into B bar plus B into A bar as well. Basically just I inverted it, nothing else. Just inverted it, nothing else. AB bar, this AB bar comes here and then this is BA bar comes here. AB is equals to BA. AB is equals to BA and A plus B is equals to B plus A. A plus B is equals to B plus A. This you can do. Okay. AB is equals to BA, A plus B is equals to B plus A. This I am writing down here. So anyhow it can be replaced. So let's check the truth table, what we get. So first I am writing A bar. What will be A bar? 1, 1, 0, 0. Bar of A. Bar of A. Bar of A. Bar of B will be 1, 0, 1, 0. Now I am doing A bar into B. A bar into B. So A bar into B. 1 into 0, 0. 1, 0, 0. A into B bar. A into B bar. So 0, 0, 1, 0. A into B bar. Now we need to add them up. I need to add both of them. 0, 1, 1, 0. So what did you understand? This was your AB. Just look at here. AB and this is your output. So A XOR B. 0 XOR 0. 0 XOR 0 is equals to 0. 0 XOR 1. This is the sign of XOR, okay? this can be replaced with A XOR, this is the sign of XOR, B plus, and then there is circle, plus and circle. Okay, 0 XOR 1 is 1, 1 XOR 0 is 1, and 1 XOR 1 is 0. So when both input are same, your output is 0, and when both input are different, your output is 1. Are you getting this point? When both inputs are same, your output is 0. When both inputs are different, your output is 1. So 0 XOR 0, 0. 1 XOR 1, 0. 0 XOR 1, 1. 1 XOR 0, 0. Getting this point? Okay, so that's why it is known as non-equivalence detector. But this definition is true only for 2 input XOR gate. This is true only for 2 input XOR gate. So non-equivalence detector it is known as. Okay, and then there is very interesting thing that 3 input XOR gate does not exist. Generally in the examination you will never see a gate like this, that I am telling y is equals to A XOR B XOR C. So this thing is wrong. Generally only 2 input XOR gate exist. 3 input XOR gate doesn't exist. But in Morris-Monod this structure is given. So it might be possible that in some of the gate question paper you can see this structure, but generally this should not come. 3 input XOR gate does not exist. This structure does not exist. Okay, but in Morris-Monod, as per Morris-Monod, in Morris-Monod you will find this particular structure, that A XOR B XOR C, but that is wrong. It should not exist in this manner. Okay, so 3 input XOR gate does not exist, neither 3 input XNOR gate exists. If you want to make 3 input XOR gate, then how you will make it? With the 2 input XOR gate. Okay, so A XOR B, here output will be A XOR B. Now this output is going into another XOR gate. So A XOR B XOR with C. So A XOR B and then XOR with C. So this is how you can make this output. Making this output like this is not possible. In simulation as well, you will never make this structure. You will get A XOR B XOR C by this only. Okay. So 3 input XOR gate does not exist actually. So if someone is asking you what is the definition of XOR gate, then you can tell this. But it is not necessary that the guy who is interviewing you knows this thing, because this is not very famous thing. So if you tell this thing to him, that it is a non-equivalence detector, and when both of the inputs are if both of the inputs are same, then output will be 0, and both of the inputs are different, then output will be 1, or output will be high. If you tell this thing to him, then he might be saying that what if it is a 3 input XOR gate. So there you cannot argue to him. So that's why I generally avoid telling this definition. So how will I tell that? Let's check out this in this particular video only. So let's proceed in this lecture. So first solve these values. 0 XOR 0 is 0, 0 XOR 0 is 0, 0 XOR 0 again is 0, 0 XOR 0, 0, 0 XOR 0, 0. Look, you will assume XOR as plus only. Assume XOR as plus only, but when you see 1 XOR 1, then you just need to think, okay, both are same, I will give 0. 0 as you assume you assume XOR as plus only. 0 XOR 1, 0 plus 1, 1. 0 XOR 0, 0 plus 0, 0. 1 XOR 0, 1 plus 0, 0. 1 XOR 1, 1 XOR 1, 1, 1, same. Then it would be 0 only. Okay. And how do I usually remember it? I will tell you. 1 XOR 0. It is like that, right? And one more I will write, 1 XOR 1. So what I would do, I will pick this one and mix it in this. I will pick this 0 and mixing it in this. 0 को उठाया 1 में डाल दिया, क्या मिलेगा? 1. 1 was there. I will pick this one and put 1 in that only. 1 को उठाया और उल्टा करके उसमें डाल दिया. Like you take it like this, उल्टा करके डाल दिया है. This is 1 and so it would be 0, right? If I write A XOR A, so I will pick A and reverse it and put it there. Basically reverse it and put it there. This is how I remember it. So it will become 0 only. If it is there A XOR A bar, so I will reverse it and put it there. So A XOR A will become 0, but bar is there. So this bar, since I am reversing it, so this bar will become something like this. So A XOR A bar is 1. This is how I remember it. It makes me remember it. Okay. So A XOR A bar is 1. In the later on this chapter only, I will tell you these things you need to remember. So 1 XOR 1 is 0. So put this 1, reverse it and mix it in 1 only. So 1 is mixed with 1, 0. 0 is mixed with 0, 0. 1 is mixed with 0. 0 is going here. Nothing is happening. So it would be 1. 0 is mixed with 1. 1 will be reversed and goes into 0. So it would be 1. Right? But same is mixed, then it would become 0. It's like interference. Constructive interference and destructive interference. So it is like that interference only. One is going into. So this is how you can remember it, because there will be a lot of things people will say that how we can remember it. But once you are habitual of this gates, then these will be a cakewalk for you. But this is just a simple way I am asking you to remember. Now 1 XOR 1, 1 XOR 1 will be 0, and then again XOR with 1. So 1 XOR 0, it would be 1. 1 XOR 1 will be 0. 1 XOR 1 will be 0. And then again XOR with 1, that would be 1. Then again XOR with 1. So 1 XOR 1, that would be 0. Are you getting this point? Look, 1 XOR 1 is 0. Then there is an XOR sign. And let's just solve this value. 1 XOR 1. Again it is 0. 0 XOR 0 is 0 only. So no matter how many zeros are there, it will always be 0. But did you notice one thing here? What did you notice? When there are odd number of ones, then answer is 1. And when there are even number of ones, answer is 0. 1 XOR 1 will be what? 0. But if I do 1 XOR 1, XOR 1, XOR 1, XOR 1. So 1 XOR 1 will be 0. And then there is again 1 XOR 1, that would also be 0. And then again XOR 1. So 0 XOR 0 will be 0. 0 XOR 1 will be 1 only. So if there are odd number of ones, then it is known as, so if there are odd number of ones, then answer will be 1. But if there are even number of ones, answer will be 0. That's why your XOR gate is known as odd number of ones detector. So in the examination, in the interview, they are asking you what is the meaning of XOR gate, then you will tell that it is odd number of ones detector. So that would be a good definition, irrespective of the inputs. So XOR gate is a odd number of ones detector. If at the input I am getting odd number of ones, then my output will be high. If at the input I am getting logic high odd number of times, then my output will be high. That's it. This is the correct, and this will be the correct answer. Okay. Now let's see this question. Odd numbers of one detector. 1, 2, 3. 3 times 1 is there. Answer will be 1. Look at this one. 1, 2, 3, 4. 4 times 1 is there. Answer will be 0. And you could have solved it as well. No need to mug it up. Okay. Basically, if I write A XOR B XOR C, so I can replace these values. C XOR A XOR B. Anywhere I can replace those. This can come here. This can come here. So what I would do, I will keep all ones aside. 1 XOR 1 XOR 1, and then all zeros aside. No matter how many zeros are there, they will become 0 only. How many zeros are there, they will be 0 only. So this will be replaced as 0 only. Now 1 XOR 1, it will be 0. XOR 1, XOR 0. So 0 XOR 1 will be 1. That's it. This is the correct answer. You can solve it as well. All the ones you take one side only. They are even. 1 XOR 1, 0. XOR with 1 XOR 1, 0. 0 XOR 0, all are 0 only. So it would be 0. So this way you will be able to write down the correct answer quickly. Or you can remember it is odd number of ones detector, which I have already written in the next page. So XOR gate is odd number of ones detector. So if let's just say I give you one more example, will you be able to write it down quickly? Look, you might be forgetting this thing, but you will not be forgetting how to solve these kind of problems. I told you, take all ones aside. So 1, 2, 3, 4, 5, 6, 7. 7 ones are there. You know 1 XOR 1 is 0. Then another 1 XOR 1 is 0. Another 1 XOR 1 is 0. So 6 ones will make 6 ones are there. 6 ones will make 0 only. 1 XOR 1, 0. 1 XOR 1, 0. 1 XOR 1, 0. Only this is left. So 0 XOR 0, 0, 0 will be there. XOR 1 and then XOR, more zeros will come. But there is no meaning of that. So basically 1 XOR 0 is left. So answer will be 1. So from here you got to know that there are odd number of ones. So it is odd number of ones detector. Because in the examination you will be forgetting it. If after 5 days I come to you and I ask you what is XOR gate? Odd number of one detector, even number of ones detector, even number of zero detector, or even number of, or odd number of zeros detector. Okay, then you will think 0 or 1 or odd, even, like this you will think. But when you take the example, okay, if there are all zeros, then there is always answer will be 0. What I mean to say is, if there are even number of zeros or there are odd number of zero, answer is 0 only. So you cannot say it is odd number of zero detector or even number of zero detector, because for both even input as well and odd input as well, your answer is always 0. So you cannot differentiate. Even if there is odd input or even if there is even input, your answer is 0. So here you cannot differentiate, because always it will be 0. But if there are odd number of ones, then you will think, okay, if there are 3 ones, 1 XOR 1 will make 0, 0 XOR 1 will be 1. Okay, so if there are odd number of ones, my output is 1. If there are even number of ones, 1 XOR 1 is 0, 1 XOR 1 is 0. Okay, 0 XOR 0, it will be 0 only. So if odd number of ones are there, my output was 1. So it is odd numbers of ones detector. So better than mugging it up, you keep it in mind. So I have seen a lot of guys forgetting this thing, odd number of ones detector, because XNOR gate will also come there, right? Now XNOR gate will also come, so there the scenes will be different. So a lot of guys forget it. So if we better keep it in mind, then it will be more clear to us. Now we will see the switching circuit. So for this switching circuit, we will use a different kind of switch that is known as two-way switch. So if my A is connected to B, then I will assume the switch to be on. And if my A is connected to C, then I will assume the switch to be off. It can be other way around as well. Like if A is connected to C, then it would be on. A is connected to B, then it would be off. It will be given in the question. Whatever the question is there in your examination, it will be given that if A is connected to B, then you consider it on. On means 1 and off means 0. So it will be given in the question. Okay. So if S1 is on and S2 is on, that means A is connected to B and this B is connected to A. So what will be the circuit? This is V in, A is connected to B, A is connected to B and B is connected to A. So this path I am getting, this complete path I am getting. So this wire is completely shorted. Are you getting this point? This path I am getting, this path I am getting. So this wire is completely shorted here. And then there is a bulb. So current goes here and it flows from here. The bulb will not turn on. The bulb will not have any current because the complete current is flowing from this short circuit path. So bulb will be off. Let's do the next thing. In the next structure, what they are saying, A is connected to S1 is on and S2 is off. So A is connected to B. A is connected to B. But S2 is off. That means A is connected to C. 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 So do you have any path? This is the input. Do you have any path? The current will come here. It will not go here because this is open circuit. Are you getting this point or not? A is connected to B and B is connected to, sorry, and A is connected to C here. Here it is connected to B and here is connected to C. So the current comes here, it cannot flow here, right? Because there is this open circuit path. This is open circuit path. Here also there is open circuit. So no current will flow here as well. So the current will go into bulb directly. So bulb will turn on. Bulb will turn on. Do it on your own. Do the third one on your own. In the third one, what is happening? A is connected to C. A is connected to C because S1 is off. That means A is connected to C. A is connected to C. And A is connected to B. A is connected to B. S2 is on. S2 is on means S2 is on. That means A is connected to B. A is connected to B. So will any current come here? Because this is open circuit. This is open circuit, so no current will come here. This is also open circuit. No current will flow here. So the current will flow in this manner. So bulb will turn on. Bulb will turn on. And what about the last one? If both are off means A is connected to C. A is connected to C. And here also A is connected to C. So this will be the path. This will be the path. So current can flow here as well. Okay. And the bulb will not turn on. Current can flow here. So bulb will not turn on now. The bulb is not turning on. So it would be off. So here you can see 1 XOR 1 is 0. So this is XOR gate only. If both are on, if both are high, then output is 0. If both are low, then output is 0. 1 is high, 1 is low, 1 is high, 1 is low, then output is 1. So this is the XOR gate. So this is how we make XOR gate. Right? Well and good. So some properties that this I have already told. A XOR B is equals to B XOR A. Just the reverse. A XOR B XOR C would be equals to first A XOR B and then you take the XOR. Then first you take A only, then you take the XOR. Basically anywhere you can put the bracket. That's it. Okay. Now XOR gate using basic gates. What you need to make? A bar into B plus A into B bar. So what is my target? What I need to make? A bar into B plus B bar into A. So A bar and then here goes A bar into B. This is my A, this is my B. A bar into B. And what else I need to make? B bar into A. So take invert of that, B bar into A. Then this A comes directly. B bar into A. And then both of them are added. So both are added. So A bar into B, B bar into A, and both are added. We will make this structure using NAND gate and NOR gate as well. But later on in the next lecture, using NAND gate, we will make this structure using NAND gate and NOR gate, but in the next lecture. So this is all about our XOR gate. XOR gate using basic gates. So basically A bar comes here, this will be your A bar, this will be your B bar. So A into B bar, this is A into B bar, and this is A bar into B, and both are added. So A B bar plus A bar B. Okay. Now important observations that I have already told. A XOR A. So let's do it. First as it is, bar of the second one plus second bar of the second one plus first as it is. So A into A bar, what that would be? I have told this thing in the last lecture only. A into A bar 0 plus A into A bar 0. That would be equals to 0. So A XOR A. So that you need to remember. A XOR A is equals to 0. I told you, how will you remember? A goes in here. So A goes in here, so 0 is left. A XOR 0. Take XOR as plus only. So A XOR 0 will be 0. Or you can take in this manner. A into bar of 0 will be 1 plus, or let's write it more. First as it is, bar of the second one plus bar of the first one and second as it is. So A into 0 bar will be 1 plus A bar into 0. A bar into 0 will be 0. A bar into 0 will be 0. So that would be equals to A. Basically A XOR 0. 0 goes in, so it would become A only. A XOR 1. So A into bar of 1 plus bar of A into 1 as it is. Bar of 1 is 0. A into 0 plus A bar into 1 will be A bar only. So A into 0 is 0. This would be A bar only. So A XOR 1. So what will happen? This 1 will go here and it will act as bar. Are you getting this point? This was A XOR 1. So 1 goes here and it will become bar. 1 is becoming like this. 1 is rotated 90 degree. 1 was there, it is rotated 90 degree. So it is A bar. So A XOR 1 is A bar. Now A XOR A bar. A XOR A bar. So this goes in, but this bar is left. So that will be rotated 90 degree. So answer will be 1. This is the way I am telling. This is just the way that you can remember. Otherwise you can derive it as well. But in the examination, a lot of variables will be there. So you will not be deriving there. Okay, you need to remember it. So first one as it is, bar of the second one. First one as it is, bar of the second one, plus second one as it is, bar of the first one. So A into A is A, plus A bar into A bar is A bar. So A plus A bar is 1. In the next lecture, in the last lecture only I told you A plus A bar is 1. So what you have to remember? These are the final answer that you have to remember. A XOR A bar will be 1. Now this is very interesting. If A XOR B is C, then what will be A XOR C? What will be A XOR C? So let's try it out. What you can replace? A XOR. What is C? C is A XOR B, right? C is A XOR B. C is A XOR B. I can open this bracket. A XOR A XOR B. What will be A XOR A? A XOR A. It will be 0. A XOR A. A XOR A is 0. So it would be 0 XOR B. And what will be 0 XOR B? That would be equals to B only. So that's it. This is the answer. 0 XOR B will be 0. So what did you understand from here? If A XOR B is equals to C, then A XOR C is equals to B. This is the first one. Or instead of A, I can replace C as well. C XOR B is equals to A. Okay. Basically, if I had written B XOR A is equals to C, if I had written B XOR A is equals to C, then these two can be replaced. Not these two can also be replaced. Okay. So C XOR B is equals to A, or C XOR A is equals to B. So these properties you will have to remember. Okay, let's see more interesting thing about XOR gate. More interesting things are there. Let's solve this. Four A's are there in XOR gate. So A XOR A is 0. Then another XOR. A XOR A is another 0. So 0 XOR 0 is 0. So A XOR A XOR A XOR A is 0 only. A XOR A is 0. Then XOR with again A XOR A 0. Then again A XOR A, again XOR 0. That would be 0. Even number of A's are there, answer is 0. A XOR A is 0. And then XOR with A. So A XOR 0 will be A only. Initially A XOR A 0. XOR A XOR A is 0. And then simply A. 0 XOR 0 is 0. And then XOR with A. A XOR 0 is A. So if odd number of A's are there, answer is A. That's why it is known as odd numbers of one detector. So A XOR A XOR A, in that manner it will go. If there are even number of A's, answer will be 0. If there are odd number of A, answer will be A. Are you able to understand this point? So this is also, you can keep in mind. You don't need to remember these things. You can keep in mind. Okay, even numbers are coming, then A XOR A 0, 0, 0, 0, 0 XOR 0 will be 0 only. If odd numbers are coming, then 0, 0, 0, but one A will be remaining. So that will be the answer. So you can just keep in mind. Nobody mugs it up. I remember these things just by pick the A, mix it, 0. Pick 0, mix it, the same value will come. Pick 1, mix it, it will be bar. Pick A bar, mix it. So A and A will be 0, but there is bar, so that would make it 1. More interesting thing will be there. More interesting things will be there, but we will cover that later on. But first, let's see about EXNOR gate. So EXNOR gate we will see. So what is EXNOR gate? EXNOR gate is simply XOR gate plus NOT. So this was our XOR gate. and then bar will be there. That's it. XOR gate and then bar. It is denoted as A dot and then circle B. This is how also it is denoted. And what will be its output? That would be A bar, B bar plus AB. Let's see how do we get it. A bar B plus AB bar, and then whole bar is there. Do you remember De Morgan's theorem? X plus Y bar, that would be written as X bar plus Y bar, right? So take bar of this, sorry, there will be dot, X bar dot Y bar. So take bar of this and then take bar of this. Now what is this? X into Y bar. So that can be replaced with X bar plus Y bar, right? So A bar, it would be A plus B bar into A bar plus B. Now multiply this. A into A bar is 0. A into B is AB plus A bar into B bar is A bar B bar, and B into B bar is 0. So what you are left with? A bar B bar plus AB. If you are not able to solve it, no need to worry, because we will see a lot of examples of De Morgan's theorem in the next part of this video. Not of this video, in this chapter only we will see a lot of examples of De Morgan's theorem. So there you will be habitual, but here also you can build the habit. X plus Y bar and X bar dot Y bar. Then you need to take bar of this. So two variables are there, bar of the first one plus bar of the second one, and then simply the multiplication. A into A bar is 0. A into B, B bar into A bar plus B into B bar will be 0. So A bar B bar plus A B bar. So just the bar we are taking, nothing else. Now what is the what will be A bar here? It would be 1 1 0 0. What will be B bar? That would be 1 0 1 0. What will be A bar into B bar? So 1 0 0 0. What would be AB? 0 0 0 1. And what would be the addition of both of them? 1 0 0 1. Okay, so what you are seeing, this is equivalence detector. If both the inputs are same, then output is 1. If both the inputs are different, output is 0. But generally I do not solve EXNOR problem by this thing. How do I usually solve that? I will tell you. So 0 XNOR 0 is 1. 0 XNOR 1 is 0. 1 XNOR 0 is 0. 1 XNOR 1 is 1. Solve this. 1 XNOR 1. 1 XNOR 1 will be 1. 1 XNOR 1 will be 1. And then again XNOR with 1 will be 1 only. Right? 1 XNOR 1 will be 1. Then again XNOR with 1. Then again XNOR with 1. So 1 XNOR 1 will be 1. 1 XNOR 1. Same. Equivalence detector. XNOR with 1 will be 1. So no matter if even number of inputs are there or odd number of inputs are there, it is 1 only always. If there are even number of ones or there are odd number of ones, output is 1 only. So you cannot say it is even number of ones detector or odd number of ones detector. But let's see in the case of 0. So 0 XNOR 0 will be what? 1. Equivalence detector. 0 XNOR 0 will be 1. And 1 XNOR 0 will be 0. So answer is 0. Right? 0 XNOR 0 will be 1. Then again XNOR. 0 XNOR 0 will be 1. 1 XNOR 1 will be 1. So answer is 1. So in case of 0, if there are odd number of zeros, then answer is 0. But if there are even number of zeros, answer is 1. So XNOR gate is known as even number of zeros detector. Okay. So let's write down both of the things. XOR gate was what? Odd number of ones detector. In one number of problem, this can be asked in MCQs. That what is XOR gate, what is XNOR gate. XNOR gate is called as, XNOR gate is called as. Okay. So in XNOR gate, you cannot define by 1. Because why you cannot define by 1? Because in both of the cases you are getting 1 only. But here in both of the cases you are getting different. If odd number of zeros are there, your answer is 0. If even number of zeros are there, your answer is 1. So it is even number of zeros detector. So in MCQ it can be asked, but even if you forget, you can derive it in the examination and then tick the correct answer. Deriving will take 30 seconds. You will see, okay, 0, 0, 0, and then you will be able to derive it. Okay, let's solve this. 1, 2, 3. Odd means 0. 1, 2. Even means 1. But in the examination I will not be doing this. I will be solving it. 1 XOR 0. What that would be? 0. Sorry, 1 XNOR 0. And 0 XNOR 1 will be 0. And then again 0. 0 XNOR 0, 1. 1 XNOR 0. 1 XNOR 0 will be 0. That's it. This is my answer. Okay. In the examination, I will not be doing by this method. I will tell you one easiest method. By that, you will not have to solve EXNOR calculation any day. Okay. In this lecture only, I will tell you that method. So 1 XNOR 0 will be 0. XNOR with 1 will be again 0. 0 XNOR 0 will be 1. 1 XNOR 1 will be 1 only. So answer is 1. In the examination, I will not be solving by this method. There will be another method that I will tell you. Now very interesting observation will come, and this is the method by that we will be solving in the examination. So first tell me what will be A XOR B. So 0 XOR 0, 0. 0 XOR 0, 0. 0 XOR 1, 1. 0 XOR 1, 1. 1 XOR 1, 1. 1 XOR 0, 1. 1 XOR 0, 1. 1 XOR 1, 0. 1 XOR 1, 0. Right? Now let's do A XOR B. So just the bar of this will come, right? Or we can solve it as well. 0 XOR 0, 1. 0 XOR 0, 1. 0 XOR 1, 0. 0 XOR 1, 0. 1 XOR 0, 0. 1 XOR 0, 0. 1 XOR 1, 1 XOR 1, 1. 1 XOR 1, 1. Let's do A XOR B XOR C. A XOR B XOR C. XOR of both of them. So 0 XOR 0, 0. Right? 0 XOR 0, 0. 1 XOR 1, 0, 1. 1 XOR 0, 1. 1 XOR 1, 0. 0 XOR 1, 1. 1 XOR 1, 0. 0 XOR 0, 0. 1 XOR 0, 1. Let me check if I am doing it correct. 0, 1, 1, 0, 1, 0, 0, 1. Yeah, it is correct. Now what I need to do? A XNOR B with this XNOR. Shall I do only the shall I do simply the bar? Shall I simply use not get here? Shall I simply use not get here? No, this is not I need to do, because this is A XNOR B with XNOR C. So A XNOR B with XNOR C. So this I need to do. 1 XNOR 0 will be 0. 1 XNOR 1. 1 XNOR 1 will be 1. 1 XNOR 0 will be 0. Sorry. These two I need to do. 0 XNOR 0 will be 1. 1 XNOR 0 will be 0. 0 XNOR 0 will be 1. 1 XNOR 0 will be 0. 0 XNOR 1 will be 0. 1 XNOR 1 will be 1. What did you see here? What did you see? That A XOR B is bar of A XNOR B, but A XOR B XOR C is equals to A XNOR B XNOR C. So for even number of inputs, both are bar of each other, but for odd number of inputs they are the same. So XNOR you can replace with XOR if there are odd number of inputs. Are you getting this point? So this is the thing I have written. For even number of inputs, XNOR is equals to XOR is equals to XNOR bar. But for odd number of inputs, XNOR and XOR are equal. Okay, so very interesting point. So A XOR B, I can write it as A XNOR B bar. But A XOR B XOR C, I will write it as A XOR B XOR C. Here I will write it as A XOR, sorry, I will write this as A XOR B XOR C XOR D bar. But here I will write both are equal only. One more interesting thing I will tell you, that A XOR B XOR C bar, is that equals to A XOR B XOR C? No, not at all, because both are same. Without bar both are same. Without bar both are same. So it is not equals to this value. How will you make this one? How will you make this? How will you make this? So what I would do, I will get this, okay, then this I will get, and then one inverter I will connect. So this is my A, this is my B, this is my C. So this will be A XOR B. So here what I will get, what this value will be, A XOR B XOR C. So eventually then this will be my Y. So my Y will be A XOR B XOR C. Or how I can write Y? Think about it. Can I write Y as this, A XOR B and bracket here and XNOR C? Say yes or no. Did you understand this point? What I am doing is, this bubble was there, no? This bubble was here, right? This bubble was here. So this bubble can come here. This bubble can come here. If this bubble comes here, that means it is acting as a XNOR gate only. And what will be XNOR of A XOR B and C? XNOR of A XOR B and C. What that would be? A XOR B XNOR of C. So A XOR B XOR C and then bar, sorry, would be equals to A XOR B XNOR C. Are you getting this point? This is the point where I am getting this value. Okay. At this point I am getting this value, and then there is a bar. Then there is a bar. So here I will get A XOR B XOR C bar. But if I make this as XNOR gate, then it would be A XOR B XNOR C. So this is also a very interesting thing. Okay. So what did you understand here? For odd number of inputs, both are same, but for even number of inputs, both are bar of each other. So this was very interesting point, very interesting conclusion. So if you need to solve these kind of problems, so what will be the first thing I will be doing? I will check the number of inputs. 1, 2, 3, 4, 5. Okay, 5 inputs are there. I can replace dot with XOR. And I am very much comfortable with XOR. So then I will be solving XOR gate very, very easily. So 1 XOR 0, 1. 1 XOR 0, 1. 1 XOR 1, 0. 0 XOR 0, 0. Answer will be 0. Here again I will count the input. They are 5 only. But let's just come here. Here I will count the input. Okay, there are 4. 1, 2, 3, 4. There are 4 number of inputs. So what I will do? I will replace with XOR only. I will replace it with XOR, but I will remember one thing. Whatever the answer I will get, I will take bar of that. So 1 XOR 1, XOR 1, XOR 1. I know I will get answer 0, but I need to take the bar. So 0 bar will be 1. So this is how I will be solving in the examination. I will replace XNOR with XOR, but if even number of inputs are there, I will take the bar. If odd numbers of input are there, I will not change my answer. So this is how I will be solving in the examination. Okay. So this you can do in your examination. Switching circuit, this you can solve on your own. So this is the same kind of switch there, which was connected in parallel. Now it is connected in series. So simply, if it was connected in parallel, like this it was connected, then I was getting this answer. Now if it is connected in series, then I will simply get bar of it. Basically, if one switch is connected in parallel and I am getting answer as A bar, then if it is connected in series, then I will get answer as A bar of bar. So that would be A. So similarly, if it was connected in parallel, I was getting answer as A XOR B. Now if it is connected in series, I will get bar of that. That would be the answer. Okay. So you can do it on your own. If both are on, If both are on, that means if both are connected to B, then a bulb will turn on. If one is on, one is off. So one connection here, one connection here, the switch will be open circuited, so it would be off. One is off, then one is connected here, another is connected here, so no complete path is there, again off. If both are off, that means this is connected to C, this is also connected to C. So both are connected to C, that means bulb will turn on. So it would be A XNOR B. Okay. Some properties: A XNOR B is equals to B XNOR A, and A XNOR B XNOR C, that can be replaced with A XNOR and B XNOR C. Anywhere you can put the bracket. Okay. XNOR gate using basic gate. XNOR gate using basic gates. So what I need to implement? I need to implement Y is equals to A bar B bar plus AB. So this is your A and this is your B. So here you are getting AB. Then this A goes here in terms of bar. This is your A bar. And then B goes here in terms of bar. This is your B bar. So here you are getting A bar B bar. And there is this OR gate, which will just do the addition. So it would be AB plus A bar B bar. Well and good. Okay, very easy. Now A XOR A. I will treat it A XNOR A. I will treat it as XOR gate. So A XOR A is 0, but XNOR is there, so answer will be 1. A XOR 0 is 0. Sorry, A XOR 0 is A, but XNOR is there, answer will be A bar. A XOR 1 is A bar. A XNOR 1 is A bar, but this XNOR is there, then bar will come. So A will be the answer. You can solve it on your own as well, that A XOR A. So bar of both of them plus without bar. So A bar plus A. A bar plus A is 1. So you can solve in this manner, but you need to remember. How will you remember? Two inputs are there, that means even number of inputs are there. So in the mind I will think XOR, but I need to take the bar of that. A XOR 0 is A, then bar of that will be A bar. A XOR 1 is A bar, then bar of that will be A. A XOR A bar is 1, bar of that will be 0. That's it. This is how I need to think in the examination. If A XOR B is C, then what will be your A XOR C? A XOR C will be what? A XOR C can be replaced with A XOR B. That would be A XOR A XOR B. So A XOR A will be 1. And 1 XOR B will be what? B. 1 XOR B will be B. So A XOR C is replaced with B. So here basically A XOR C is equals to B and B XOR C is equals to A. That's it. This is not the answer. This is how we can replace it. Okay. Now let's solve these problems. A XNOR A. So in the mind I will think of XOR gate. A XOR A is 0, but I need to take bar, so it will be 1. These inputs are 3 inputs, that means these are odd inputs. So in the mind I will think of XOR gate only, and that will be my answer. A XOR A is 0, 0 XOR A, that would be A only. Here I will get 1 and here I will get A. You can do it on your own. So if number of inputs are odd, then my answer is A. And if number of inputs are even, then my answer is 1. So you don't need to mug it up in the examination, you will be able to do it on your own. Right? Okay, very easy. Let's move towards next important properties. Very, very important property it is. Very, very important. So let's solve this. A bar XOR with B. So first as it is, bar of the second one plus bar of the first one, A bar bar, and second as it is. So what I am getting? A bar B bar plus AB. That can be replaced with A XNOR B, or it can be replaced with A XOR B bar. So if there is bar on 1, then whole bar can be taken. So how this can be done? If there is bar on 1, then whole bar can be taken. Then there is bar on the another one, then another whole bar will be taken. So 2 bar will cancel out each other. So A XOR B only. You can solve it as well. A bar XOR B bar. So first as it is, bar of the second one plus bar of the first one, that would be A only, second as it is. This is A XOR B only. So if there is bar on 1, the whole bar can be taken. Same goes for this one. You can solve it. You can solve this one. Bar of the first one, bar of the first one, and the bar of the second one plus as it is. This is XNOR gate. In XNOR gate, what do we do? In XNOR gate, what do we do? Bar of the first one, bar of the first one, and then bar of the second one plus both as it is. A bar B bar plus AB, bar of the first one and then both as it is. So AB bar plus A bar B. So it can be replaced with A XOR B, or I can write A XNOR bar. So there was a bar and then whole bar is there. One bar will be taken as whole bar. So what will happen to this one? One bar is there. So because of this bar, one complete bar will come. Because of this bar, another complete bar will come. So it would be. So that's it. So this is a very important property. If bar is there on one variable, then whole bar can be taken. Okay. So you will remember it, right? So let's see what we have. So now we will see example of all these in assignments. More examples can be there. Like 3 variables are there, then how we will deal it. So more examples can be there. So let's take one example. So if I write A XOR bar of this, now how you can replace it? So can I assume it as A bar XOR X, where my X is B XOR C? So can I write it as A XOR S? Why I can write it in this manner? Because whole bar I will be taking. Basically, I skipped one step. That step is A XNOR X whole bar. So that can be replaced as A XOR X. And what is our X? B XOR C. So this can be replaced with this. So these kind of questions will come. So basically, you will just have to make it 2 variables. If you are able to make it 2 variables, then you will be able to solve it. Okay. No need to worry about it. These kind of questions are very easy. So NOT gate and buffer using XOR gate. So let's just say if this input is A and this input is 1, what will be your output? Y. That would be A XOR 1, because this is XOR gate. So this answer would be A bar. So what is this? This is acting as NOT gate. This is acting as NOT gate. Very simple thing, very easy. If here I am having A and here I am having 0, so what will be my output? A XOR 0. So that will be A only. So your input was A and output is also A. So what is this? This is acting as buffer. Right? If this is A and this is 1, so Y will be A XNOR 1. So that will be A only. So what is this? This is also buffer, because A XNOR 1 is A only. If this is A and this is 0, so what will be your Y? Y will be A XNOR 0. That will be A bar. So what is this? This is NOT gate. Well and good. Very easy. Okay. Now we will see this thing in next lecture, because we need our target is to implement any function using minimum number of NAND and NOR gate. So in the next lecture we will see what are their equivalent representation, because this equivalent representation we have already seen. What is this? This is NOR gate. So NOR is bubbled AND gate. And what is this? This is NAND gate. NAND gate is bubbled NOR gate. If this is bubbled NOR gate, so basically what is this gate? This is AND gate. So AND gate can be replaced with one note and then another note, right? So this can be replaced with this much of gate and then another note will come. So this is how this can be replaced. Okay. Right. So in the next lecture we will see it, and similarly for this one as well. Then we will see the basic definition of SOP and POS, sum of product and product of sum, because that will be used in our analysis. Okay. So yeah. So in this lecture there was a lot of information. So before moving on to the next lecture, or before shutting down your laptop, once revise this lecture again. Okay, revise it very fastly. You will be able to revise. You will be having the notes as well. So revise it and then move to the next lecture. Next lecture will also be very, very interesting.